Hi, today I'm going to talk to you about the Doppler effect, as it is related to waves, which I'm currently studying at school as part of the AS physics course. The Doppler effect was first thought about and noted down by Christian Doppler, who was an Austrian physicist in 1842. He proposed the idea that the Doppler effect is the change in frequency of a wave or other periodic event for an observer moving relative to its source. There's a quick diagram to show you what the Doppler effect, how it can be observed in terms of waves, and you'll understand that later on. What can it tell us? Well, it's used in lots of different everyday scenarios, but two of them which are more common is astronomy, where it is used to determine the direction and velocity of a luminous object relative to the Earth or the telescope observing it, and this is known as blue shift or red shift, which we will later go into at the end of the PowerPoint. Furthermore, if you've ever heard a siren of an emergency vehicle, they quite often sound different depending on whether the vehicle is going away from or towards you, and so you can be alerted if a vehicle is approaching you and you may have to react, or if the vehicle is going away from you and it won't affect you. Where else is it used? Well, many different places. Sirens, astronomy, temperature measurements, radar, medical imaging and blood flow measurements, velocity profile measurements, satellite communication and underwater acoustics. In depth, I'm going to go into astronomy later, but those are just some brief ways which it's used, and you can look into them further. Well, seeing as it can apply to both longitudinal and transverse waves, I decided that I'd use sound for my example and a fire truck. Sound waves are emitted by the sirens, and in this case they can be longitudinal and transverse and travel in that direction. For a stationary object, the sound waves have equal wavelengths either side of the vehicle, as shown by the green line representing the lambda. People standing either side of the vehicle will experience the same frequency of sound, and there'll be no difference if you're standing still, either side of it, above it, in any direction. It should pretty much have the same frequency. When the object emitting the waves begins to accelerate, it starts to affect the waves being emitted by it, which is where the Doppler effect comes into play. If this is the direction of movement, you can see that the waves actually begin to bunch up in front of the vehicle and are stretched out behind the vehicle, creating a shorter wavelength in front of the vehicle and a longer wavelength behind, as shown by these two lines, the yellow representing the wavelength behind the vehicle and the orange representing it in front of the vehicle. And how does this compare to our original wavelength? Well, the wavelength when the vehicle is at rest should lie directly in between these two wavelengths. In this case, the source is travelling less than the speed of sound, and therefore you will hear a slightly higher frequency pitch, and behind the truck you'll hear a lower frequency sound. You can still observe and hear the source depending on whether you're standing in front or behind it, but this can be changed depending on the speed of the vehicle, as you will see. If a vehicle was travelling at the speed of sound, or if the source was travelling with the same velocity as that of the waves being emitted in the median, the wavefronts would bunch up at the front to form one universal wavefront, and someone in front of a vehicle will not detect anything, as the waves travel at the same speed as the source, and so until the source has passed them, no waves would have reached them yet. And then as the vehicle goes past them, they'll suddenly experience a much larger wavelength version of the sound, stretched out and slightly distorted. When the source travels faster than the velocity of the waves cannot be detected until the source as the source creates an advancing wavefront which can't be detected until the source has passed the observer. As you can see here, the wave that has just been emitted is actually overtaken by the truck, and a new wave front emerges, which is slightly in front of the previous one, and therefore you get these advancing wavefront effects, which you can see here. There are equations which you can use. For the frequency of a wavelength would be 1 plus change in velocity times the emitted frequency divided by c. Or there is the change in frequency, which equals change in velocity times observed frequency over c. Now, how is this used in real life? I looked at many ways of it being used earlier, but now I'm going to look at blue shift and red shift used by astronomers to determine whether an object is moving away or towards the Earth and what its velocity is relative to ours. Now, this can be used to prove many theories, such as that of the expansion of the universe, as if every object in the sky starts moving away from us, it can be determined that they are filling into a space which is basically the universe expanding. All stars are luminous and so emit their own light. If you know what type of light they emit, you know what colours of the spectrum should be observed on Earth. But if the star begins to move, these colours get slightly distorted. For instance, if the direction of the star is as so relative to ours, the light detected by us on Earth has a higher frequency and so is blue shifted if the detected light is shifted towards the blue end of the spectrum. Whereas if it's moving away from us, it's red shifted. The opposite happens, and the light detected by us on Earth has a lower frequency and therefore shifted towards the red end of the spectrum. Here's a quick diagram to show you, with the top being unshifted light, then red shifted and blue shifted light shown, and this is for the same original light being emitted, but if a red shift occurs, shows that the light has been stretched out and therefore the object is moving away from us, and blue shift would be of an object moving towards us. Thank you.